Okay, the last spotlight for this mini spotlight segment will be Alex Elemi presenting with a great paper title, GILBO, One Metric to Measure Them All.
Hi, I'm actually Ian Fisher, not Alex Elemi. And yes, I'm here to present, to tell you about GILBO, One Metric to Measure Them All. Not surprisingly, this is joint work with Alex Elemi, and we're both at Google AI. So the problem we're tackling is that generative models are difficult to compare quantitatively across different model families. In particular, if you have some GAN that you've trained on a particular data set, how can you tell whether or not it's better or worse than another GAN on from the same data set, or a VAE even? But if you think about it carefully, you can notice that actually the probabilistic form of these generative models is the same for both GANs and VAEs. You have some prior over a latent variable z, and you have some decoder, p of x given z. So given that they have the same form, you could imagine that if we should be able to come up with metrics that take advantage of this equivalence. The particular approach that we take is to try to measure the mutual information between the observed variable x and the latent variable z. So on the first line, we just have the definition of the mutual information, but we can expand the joint distribution p of x comma z out as p of z, p of x given z, which again is just our generative model. And similarly, in the log ratio, we can expand p of x comma z as p of x, p of z given x, and simplify. And that leaves us with this posterior distribution p of z given x, which is unknown and assumed to be intractable. But we can just make a variational approximation to the posterior, call that e of z given x for the encoder distribution. And this gives us a lower bound on the mutual information between x and z, which we call the GILBO, the generative information lower bound. So we can train our encoder distribution just by maximizing the GILBO. And you maximize the GILBO by taking samples from the generative model, which is to say that training the GILBO has no dependence on the actual training data set that was used to train your GAN or your VAE. So we did some experiments on 4 different data sets: MNIST, Fashion MNIST, CFAR10, and CELEB-A. And we looked at 3,200 different GANs and VAEs trained on these data sets. And we measured their GILBOs and their FID scores, which is, I think, the most popular way of comparing GANs right now. And we'd like to particularly take a moment to thank the authors of Are GANs Created Equal, who let us use their previously trained models. Their paper is also being presented at this conference. So what makes a good GILBO? Well, it shouldn't be too small, as it is for these GANs where the GILBO is less than log the number of classes in the data set. It's clear that none of these GANs has figured out how to generate realistic MNIST digits. But it also shouldn't be too big. And so one way of thinking about what is too big would be comparing the GILBO to the best reported negative log likelihood on your data set. In the case of MNIST, that's around 80 nats. And these GANs all have GILBOs greater than 80 nats, and you can see that they've basically learned just to generate noise images. Another interesting point, though, is right around log n. So if you have a generative model that has learned to perfectly memorize the training data set, then the mutual information between x and z for that model would be log n, log the number of training samples. So it's particularly interesting to see that all of the GANs with the best FID scores cluster at log n for MNIST. Does this mean that these GANs have memorized the training set? Well, we don't actually know, but it is very suspicious. So really, you want it somewhere in the middle, and it's interesting to qualitatively compare models that have the same GAN. For instance, all the VAEs are in a small cluster of GILBOs. They're in gray in the image on the right. And if you compare the sample quality of those of the VAE's image to GANs that have the similar GILBO scores, I think you'll agree that the VAEs actually have much better sample quality. So that's interesting and somewhat surprising. So given this new metric, we might care about like how good of a metric it actually is. We can analyze this metric in terms of things like its consistency, its reproducibility, and the tightness of the variational approximation. And you might also wonder about whether or not the mutual information is infinite. It isn't, and you can come ask us why at poster 57. So give it a try. We have some code, and thank you.